All right. Good evening, everyone. My name is Keyur. I guess the introduction's already over, but I work on the infrastructure team at Etsy. And this is like a war story about building Etseek. Etseek is like a write once, read many data store that was built using core utils, fseek, fread, and fwrite. Like really basic things that are available on all Linux systems or almost all the Unix even. So basically, we have like a thing called datasets at Etsy, where we're serving data that is baked in Hadoop, like things like recommendations, spelling correction suggestions, and like auto-suggest queries, things that are really critical for features on our site, but are also constantly updated and need to be accessible in a speedy manner. And we have like two kinds of data sets. There is a key value data set where, in this case, like these are spelling corrections, like the spellings are wrong, and we suggest like the correct spellings, or like try to direct people to like certain other queries. And the other kind of data set is sorted set, where we might use these for things like similar listings, where we have like a score, like for listing ID 1, like these 4 listings might match to a certain degree, and we may want to use this to like surface some interesting data for our users. So this problem, like data sets have existed at Etsy for the last 5 years, and they've gone through like multiple iterations. The first version was in MySQL, because that was the thing that we used at Etsy, or we still do, like it's our first answer to any storage problem. And that kind of stopped scaling once we hit like a 10 gigabyte data set, because we were using the same cluster to store data sets that we were using to store like all of our user data. So we hit that wall and we couldn't scale, so we moved to Redis. Redis was a lot faster to like load a large data set, so like we could go up to I think 100 gigabytes, but Redis, as you all know, is in memory. And that was like a fatal flaw because we could only buy so much hardware to like keep loading these like giant files into memory. So the current implementation is SQLite on SSDs. SSDs have become super cheap over the years and are really good at like accessing random data. And SQLite as a format is like super compact and super fast. So that's what we've been using for the last roughly a year. But like as an infrastructure engineer, I think this graph illustrates like a problem that we all face. We think that there is a certain like rate of growth for like the things that we provide, so we have like certain available capacity, and then as we come closer to it, infra engineers add more capacity, but that just doesn't, like that actually changes the slope of the graph. As you can see, like things quickly boost to like use up all available capacity again, and you start over. So for the SQLite format, this is kind of how we were taking data from Hadoop and putting it into SQLite. So like part files are the artifacts of like a MapReduce job. They're what the reducer outputs. They could be between 100, tens of thousands of part files for a particular kind of Hadoop job. We take every one of them in parallel and convert every single one into a SQLite file, and then eventually merge all the SQLite files into one giant SQLite file that we can query from. The last step is super serial, as you can imagine, because SQLite is a really simple data store. It cannot support multiple writers at once. And that takes a really long time. Like for this 500 gigabyte data set, we're spending roughly 90 minutes, like merging 200 SQLite files into one SQLite file. And we kind of approached a point where we were taking about 18 computer hours to like convert all of our data sets into something servable. That was like really limiting to our data scientists because they couldn't iterate fast enough, and we were limiting them to how large the data sets could be in order to like build features on the site. So there were a bunch of email threads around the company about what should we do about this, how should we scale this, what are our answers to like give to our data scientists. And I kind of got nerd sniped into this problem. I'm not on the team that like works on this. But I guess I started thinking about it from like, what is like the simplest thing that will work here? We're not trying to solve a super complicated problem. It's a key value store and a sorted set, not that difficult. So what about a binary search? So our problem is very like classic binary search. You write it once, just like a phone directory, and then you read from it many, many, many times. And then you throw away the phone directory every time there's updates, and you start using the new phone directory. So binary search might actually fit us really well. And SQLite provides a bunch of guarantees that we don't actually need. We don't need SQL, we don't need a full SQL engine. We don't need crash safety. We don't need transactionality. All the things that actually make SQLite great are things that we don't need. So just a quick refresher on binary search. So you have a sorted array. This is 4-byte ints. You say you're looking for 24. You start in the middle. There are 14 elements, or I think 13 elements, so 66 in the middle. And then you halve the array, so you land at 18, and then halve again, and you land at 24, and you've found the thing that you want. So this is really fast on a computer because the CPU is able to move in increments of 4 bytes, multiples of 4 bytes, actually. And the thinking was so we obviously cannot use RAM because we already tried that with Redis. Can we use disks to do this? And it actually kind of fits well in a file too, because if your file is fixed format, so in this case, every line is 5 bytes. I'm not showing the new line character at the end, but every line is 5 bytes. So you can move in increments of, or multiples of 5 bytes and actually do the same binary search in a file as long as it exactly matches. Every line remains 5 bytes. And the file is sorted. So this was the first dummy implementation that I wrote to convince myself and others that it was actually worth it. And this was actually the entirety, I'm skipping the opening the file part, but this was the entirety of the implementation. You read a line from the pipe, break it up into key and value. And because our keys can be arbitrary length, and because we need a fixed file format, we'll just hash them, use MD5, nothing complicated. And then in line 11, create an array of all the keys in the file, sort them, and write them out in line 13. And write them out in a fixed file format. So the hash followed by the part file name that you're processing, and offsets into the part file where you will find the data that you're looking for. And because we have hundreds or thousands of part files, they eventually also need to be merged. And here is where core utils comes in. Sort is a really amazing program that is well tested, has existed for years, and is really, really good at sorting, as you would expect. And sort actually is really clever because it can deal with pre-sorted data without redoing any of the work. So because we wrote out our index files in a sorted manner, we just have to merge a bunch of index files together, and they're already sorted, so you just need to go into every index file, compare them against every other line on the line that you are, and then write it into the output file if it is the smallest entry, and then do that for every line in every file. So it's a O of n operation through all the files, and really, really fast. And it only takes 5 minutes-ish to do the thing that SQLite took 90 minutes to do. So why is SQLite slower? So I guess I already touched on this a little bit. SQLite is a full embedded database. It uses a binary tree to store data, and it offers a ton of fault tolerance. And these are the kinds of things that we don't really need in our case, because we're okay throwing away stuff. For example, if the box that we were creating this data set on crashed, we are happy to just start over. We don't have to recover the data to start over from a particular point. The only concession I made from the original code that I showed was I did add checksums for every data entry, because SSDs, we were using consumer SSDs at this point, and they may have bit flipping issues, and you definitely don't want to serve bad data to your users. So there is now an added Adler32 checksum at the end of every line to just make sure that the data that we wrote is the data that we're reading back. So yeah. So that was the key value store. But then how do you extend this idea to do sorted sets? As you remember from a sorted set, every key can have multiple scores and multiple values associated with the score, and you want to return data, let's say, in ascending or descending order. So in order to explain this, I'll quickly touch on the thing called endianness. As programmers, we normally do not have to think of this, because you're working on, most people are working on x86, it's always little endian, not a problem. But little endian is different. So like most humans like who speak English learn to read things from left to right. So 4 is like 0000004. And 256 is what is up there in hex. But little endian completely flips this order. It is from right to left. And this really matters when you're doing a thing called memcompare. So memcompare does not take endianness into account. It always compares from left to right. So if you were to compare 4 and 256, but as little endian byte arrays, 4 would be greater than 256, which is totally wrong and not what you want. So remember the endianness bit while I go into floating point numbers. So like the scores are always floating point numbers. Because I don't have a lot of time, I'm just going to touch on 32-bit floating point numbers. The number, like 32 bits are divided into a sign bit, an exponent, and a fraction. What do I mean by that? So the thing to remember is, or the way to understand floating point numbers, how they're represented in binary, is to understand like a normalized scientific notation. Basically, if you wanted to represent 260 in base 10, then it would be 2.6 into 10 power 2. So here the fraction is 2.6 and the exponent is 2. And 26 would be 2.6 into 10 power 1. The idea behind this is that you can most times you can get away with just comparing the exponent. As long as the exponent of A is greater than the exponent of B, you know that the number is greater than the other without having to compare every single bit in the thing. So IEEE 754, which is the standard floating point representation, is based on the same idea except in base 2. So in this case, like 260 to the base 10 is that number. And when you're multiplying it by 2 power 8, you're just shifting the decimal point 8 times over, just like you would with a base 10 number and 26. So in this case, too, like you can just compare the numbers by comparing the exponents without having to even worry about what the actual decimal may be. And David Leibowik, Recurse Center alumni, has a really, really good GitHub article about this stuff. Like I'm skating over a lot of detail here, and that you should go check it out. So to reiterate, floating point numbers split up into like a number of bits, and you need them to be in, actually, I'm stepping forward. So I'm going to make an assertion here that I'm not going to prove, but if F1 and F2 like are positive floating point numbers, if you interpreted their bits as integers, call them I1 and I2. I1 and I2. If F1 is less than F2, then I1 is less than I2. This kind of intuitively makes sense when you consider this, where the exponent is before the fraction. So if you just think of numbers that are not actual decimals, in this prior example, for example, 8 is greater than 4, so you know that 260 is greater than 26. And that is the property that we're going to use. So if you convert, or if you take the 8 bytes of a floating point number, convert it to big endian, and pass it to sort, it will sort lexicographically correctly. So just to go over that one more time, they have to be in big endian format because that is how memcompare works. And they have to be considered integers because that is like the trick, like the beauty of the IEEE 754 format, that this assertion that I'm making is always true. And again, go to David's blog. He explains it. He has a proof for it, which I cannot show right now. So if you want to store a Z set, or basically a sorted set, you just need to add this floating point number as your key to sort. So 16 bytes represent all, like a 64-bit float converted into hex. And it's like, as an argument to sort, just say like, don't sort just the first 32 bits, which are the MD5 of the key, sort the first 48 bits. And what you'll end up with is a file that is perfectly sorted both by key and by the score. And you can just read it straight out and return it back to your user. The data will be in the correct order. So as some of you may be wondering, why are we doing all of this in core utils and like just kind of duct taping a bunch of Linux tools? Hadoop is like the place to do sorts. There is like a reason for this. Like most sorts eventually serialize down to one reducer because you need to merge all the results together. And that may have like negative impacts on our cluster because we do write really, really large jobs. And at least initially, I wasn't comfortable making such a giant change to like the way we do things in our Hadoop cluster. So in the future, when an expert from Hadoop looks into this, we may totally move all of this stuff into Hadoop land. Basically, like for every part file, like creating a range file, which specifies like, as long as all the part files are perfectly sorted, we just need a range file that specifies what are the ranges in every single part file, binary search all the range files, and you have your answer. So at some point that would happen. All of this would then move into Java or something. It's currently in PHP. That's it. Thank you.